Right. Checking 1, 2, 3. Right, good. Yeah, right, I'm good. It's Friday. By the way, I have a meeting at 10 o'clock today, so it's going to be a shorter stream than 3 hours usual. Yeah, we probably stop at 9:40, 9:45 or so. Alright, we'll continue from last time. Just a second. Right. So, we start with section 8.4. So on recap, this section is called trigonometry substitution. So we're going to let a variable equal to a trig function, and the beginning of section 8.4, we have 3 different cases. The first one, where we have a constant square minus x squared, in which case we let x equal to a sine theta. A second one, where we have a constant square plus x squared, that will let x equal to a tangent theta. And case number 3, where we have a variable square minus the constant square, we're going to let a equal to secant theta. Which each substitution, that different things that we have to worry about. Now, the reason we use trig substitution is this. From 2 terms, when we do the trig substitution, it turns into 1 term. And that's the idea about trig substitution. Usually we have a difference of 2 square or sum of 2 square. We make that substitution go from 2 terms to 1 term. Right. Now, why do we need that? Well, look at the first example here. We have the square root of 2 terms, which cannot cancel. What can cancel, however, if we can somehow turn these 2 terms into 1. One will turn 2 terms into 1. We take the square root, the square, and square root cancel out. Then we don't have to deal with the square root anymore. So that's the idea. By the way, in general, square root of the square is equal to absolute values of a. In general, they don't cancel out like this. However, when we do the substitution, we have to have some certain condition as well. Those 3 conditions. Where those are satisfied, the square will cancel the square root. Alright, so the idea here is use trig substitution to turn two terms into one, and we simplify things. And when we get to a problem like this is section 8.3, where we do the integral. This is where we have tangent and second, whatever is even, whatever is odd. We can also have the case when we have sine and cosine, when it's equal to even, when it's equal to odd. Right. By the way, this section 8.3 was in the test 1. Was in test 1. So we're not going to do that here, sorry. Right. Now, we continue. Actually, we only did this one. Right. We did this one, and what we did was we let the substitution x equal to 3 tangent theta. And we'll go from there. Now go to second. Just a second. Right, so have that. By the way, I hate to start a day with this kind of problem. It will take more than one page to do. But first, a substitution. Right. So, 3 different scenarios here. A constant square minus x squared, a constant square plus x squared, and x squared minus a constant square. Here obviously is the case number 2, where we have x squared plus a constant square. Right. So we can write like that. So that will consistent to what we have here. A constant square plus x squared, where a is 1. Right. Substitution. Substitution. We're going to let x equal to a tangent theta. A tangent theta, so just tangent of theta. Because a equal to 1. Right. And then we're gonna solve for the x. So we check derivative. Derivative of tangent is secant square, and move the theta over. We have dx equal to secant square theta d theta. Right. So we have dx. Let's take care of it. Now we need to simplify the 1 plus x squared. X is equal to tangent theta. So you have 1 plus tangent square that equal to secant square. Right, and we're going to substitute that into here, 1 plus x squared. Right. So it's good enough, right? So when we look at the form, we know the trick, the substitution that we're going to use. From there, we simplify inside, and then we solve for the x. Now substitute back into the problem. The integral will be equal to square root. Instead of 1 plus x squared, we're going to use secant square. And dx is going to be this. Right? So square root of square is just secant. Right? Like we assume that everything is satisfied, so the square cancel the square root. Once again, in general, it should be absolute values, but we assume that there's some certain condition that is positive, so it will cancel out. Now, secant times secant square, that is the secant cube. Right? So far so good. That is the idea of trigonometry substitution. We make a substitution so that we don't have to deal with the square root. Usually there's some kind of power. We go from 2 terms into 1, and we don't have to deal with the square root. That's the idea. Right? So it's not that bad if it is like this. By the way, on the test, more likely I'm going to only ask you to do this, because the part after that is section 8.3, which is already in the first test already. Right. Now, how do we do the secant cube? Well, if we're going to do that, it's going to be Now we'll go to the secant cube, and this is where I said this problem will take the whole page, because the secant cube, I think we did this problem before. So let me find that. It is the from yesterday, from Wednesday. Right. Let's see, where is that? This is in section 8.3. subsection 3 3D example 2. Right. Right. So if we go to that example, integral of secant cube is going to be that. Right. Let me copy that down here. Right. So if we're going to go back to that section, the secant cube is equal to that. Right. So that serves us like one page of calculation. We did that last time. Right. Now go back to the problem. So in the problem we have tangent is equal to x. So obviously this is equal to x. We know that. Just need to know the secant. Right. So what is the secant? Right. For that, we need to draw a triangle. Tangent equal to x, or I will write tangent is equal to x over 1. So a triangle angle theta. Right. Tangent is opposite over adjacent. So we have opposite is x over adjacent 1. The hypotenuse therefore will be square root of x squared plus 1 squared, or just square root of x squared plus 1. And then secant secant will be reciprocal of cosine. Cosine is adjacent over hypotenuse, so this will be hypotenuse over adjacent. Hypotenuse over adjacent. So that is just x squared plus 1 is the secant theta. Right. Which is, we will go here and here. So this equal to 1/2 x times square root of x squared plus 1, and then ln square root of x squared plus 1 plus x plus C. Right? So it's not that bad. The key here in this section, what you need to know is how to do this, to go from a problem into a problem of trigonometry of expression, trigonometric expression, and then we do that. Right. Right. Moving on. C. Example 3. Right. I'm going to change the problem just by one bit. Instead of 1, I'm going to change to 4. So just a tiny bit. Right, so this time what we have is x squared minus a constant square. 4 is a constant square, 2 square. Even though if it is 3, we're going to write as 1 square root of 3 square. Right. So what happens if we have x squared minus a constant square? So the beginning of section 8.4, we have 3 scenarios. And the case where we have x squared minus a squared, we're going to let x equal to a tangent, a secant of theta. So this is case number 3. Right. It's going to be a secant, right? Where's the sorry, case number 3, that is secant. Right, then we'll check derivative of that. Derivative of secant is secant tangent. Move the d theta over dx equal to 2 secant theta tangent theta d theta. So we can substitute into dx here. Right. Next, we combine the two terms into one. We're just gonna, either one. It's fine. Let's go with that. X squared minus 2 squared. X is that. Minus 2 square. Right, a square here go to it. It's gonna be 4. I just want to write 2 square. Secant square minus 2 square. Could be 4, but I just write 2 square. And then factor out the 2 square. We have secant square minus 1. Right. And of course that equal to tangent square. But of course the trig identity is tangent square plus 1 is equal secant square. So secant square minus 1 is equal to tangent square. Secant tangent square minus 1 is equal to tangent square. Right. So we're going to use that. Minus. So it will be 2 square tangent square. Right. So that where we go from 2 terms combine to 1 terms. It's essentially, it's very important. Right. Now first we still have the x, which is 2 secant theta. And then square root that one is going to be this. Dx is going to be that. Right. Now, of course, the square root and square cancel out. Like I said, we assume that it is going to be positive, and it just cancel out instead of absolute values. Of course, the secant cancel, but worry about that on the next step. And that square root of 2 square, so it's 2 tangent 2 secant of theta, tangent of theta, d theta. Right. Now, secant cancel secant, the tangent cancel the tangent, also the 2 cancel out the 2. We only left with a 2 here, and everything else cancel out. So the 2 constant can be moved outside. Still at the bottom though. And everything can sort out completely. So this problem turned out to be very nice. Not even any trig function. Will be just that. Right? So the integral of d theta, or the integral of 1, is going to be theta. Right? Now we just have theta instead of x. If this is a constant, that would be kx. But the constant is equal to 1 in this case, and theta instead of x. So we have 1/2 theta plus c. Right. Finally, what will be theta? So we go back to the original problem. We show for secant theta will be x divided by 2. So in which case, if we want theta, it's going to be secant inverse. So we have 1/2 secant inverse of x over 2 plus c. Right, it's not that bad. It will be kind of difficult for this kind of problem to fit into one screen. Yeah, but it's not that bad. Just that. Right. Okay. Once again, when we have a x squared minus a constant square, this is a substitution. And then we solve for the x and try to combine those two terms into one. Then put it back in the problem when everything cancels out. We should have a trig expression here. In this case, even better, we don't have anything. Everything cancels out. We just have that. Oh, it's not that bad. This one. Right, 2. What happens if we have the integral of x squared plus 4x plus 5, minus 5 over x plus 2 right. Right. This one's bad. For one, we have the limit, so this is definite integral. And then 2, we need to do something before we actually do the trig substitution. Right. Right. So the first thing we need to do is we have to bring this into one of those 3 cases. By those 3 cases, we mean constant square minus variable square, constant square plus variable square, variable square minus constant square. So this is not quite the right form. So first, try to make it into a square. So x squared plus 4x. We want to split that. We're going to add something, subtract the same thing. So that the first 3 will be a complete square. Right, complete square. Let's say if we have x, either plus or minus, let's do plus here, when we multiply it out, so to make a complete square, notice this term, we're going to take half of that, and then we're going to square it to get to that term. So we take half of the 4, it's going to be 2, 2 square is 4. So what we actually add here is going to be a 2 square and subtract 2 square. So that the first 3 term here, we make a square, x plus 2 square. Yeah. Just go from here back to that. And then minus 2 square, minus 5 square, 2 square is 4, minus 4, minus 5, minus 9. Right, so we do have a square minus 9, which is a 3 square, so that's good. Now, before we actually go to this, notice the substitution we make is just going to be a variable square minus a square. So instead of that, let's do kind of preliminary substitution. So what I do is I will let u equal to x plus 2. So I will turn this into just one variable. So let u equal to that. And also x plus 2 at the bottom. When u equal to x plus 2, derivative du over dx is equal to 1. Move the dx over. We have du equal to dx. And then also the limits. When x equal to 4, u equal to u equal to 4 plus 2. And when x equal to 1, u equal 3, 1 for x plus 2, 3. So go from 3 to 6. Oh. X plus 2 square minus 9. The reason is this. So I have x square plus 4x plus 2 square minus 2 square minus 5 square. This together is minus 9. Now this is a perfect square trinomial where we use that. It's going to be x plus 2 square. Now if we multiply it out, x plus 2 square x times x square, x times 2, 2x, 2x, 2 times 2 is 4. So x square plus 4x plus 4, which is this, which is equal to this. So those two are equal. So those 3 terms turn into an x plus 2 square, and then the 2 square is 4 minus 4 minus 5 is minus 9. Alright, so the trick here is how do we know the two square to be added and subtract, right? So that's what we have here. X squared plus 4x. We need to add something, subtract something to balance out. When we add something, we have to subtract the same thing to balance out. So to do that, we take half of this number, which is 2, and then we're going to square. And that's how we get the 2 square and the 2 square. Right. So just a preliminary substitution. When we do this substitution, the limits we go from 3 to 6. Integral x plus 2 is u minus 3 square, and x plus 2 is also u, and dx is equal to du. Right, it's not that bad. We have this problem. Right, now substitution. Obviously this is case number 3, where we have a variable square minus a constant square, variable square minus constant square. So it's going to be a secant of theta. So the substitution, let u, the variable, be equal to 3 secant of theta. And we'll take derivative. It's going to be 3 secant tangent, and move the theta over, du equal to 3 secant tangent d theta. I should start this one on the news page. Anyway, it's not that bad, right? Now, what's next? So we have the du, which is good. Now just need to do the u square minus 3 square, turn that into 2 terms into 1. So u square minus 3 square, u is 3 secant theta, minus 3 square. Right, square the 3 and square the secant. Usually I won't even bother to do the square, and then factor out the 3 square. And the secant square minus 1. Is tangent square. Right. As you see in this, all of this, on 3 cases, when we have that substitution corresponding, we're going to use this. That substitution, we're going to have this, and this substitution, we're going to have this. So because you see 3 square tangent square theta, right? Exactly that. So all of those three cases, we should have those three simplification. Right. Now this is the integral I. Let's continue. Will be integral from 3 to 6 square root. The u square minus 3 square is that. Right? And then the secant square, the u is 3 secant theta. Right? U is 3 secant theta. Except that is and then the du is that. I don't know where to go with this yet, but step by step. Right, the top square root cancel the square. We just have 3 tangent theta, 3 secant theta at the bottom, 3 secant theta, tangent theta, d theta. Right. So that's good at all, but just need to pay attention for one important thing. We did not make any change in the limit. So whatever the limit 2 and 6 here, that is u. So we're just going to write this limit is equal to u because we haven't changed it yet. Usually when we make a substitution, we change the limit too. But it's complicated enough. Just keep it as is. Worry about that later. Right, now, secant, cancel the secant, 3, cancel the 3, and we have 3 times tangent times tangent, tangent square. So we don't change the limit here. And then we have 3 tangent times tangent. Right, 3 tangent square. So what do we do with tangent square? Now let's go back to section 8.3. That when the power of tangent is odd, we use that. Power of secant is even, we use that. When tangent is even, well, try something else. That's not a good thing, but usually iteration by parts or Pythagorean identity. So I will go with that actually. Right, so Pythagorean identity. Tangent square plus 1 is equal to secant square. Tangent square will be equal to secant square minus 1. Let's substitute into that. By the way, let's just take the 3 outside where we added. Tangent square, secant square minus 1. So how does that actually help us? Now, actually, we're almost there. Let's split this in two. Sorry, there's a bracket. Yeah. When we split this in two, we still have the 3 on the outside. So that one, the 3 outside. Right. Now, what is the integral of secant square? The secant cube is extremely complicated. The secant is also not very nice, but actually the secant square is very nice because the derivative of tangent is secant square, so antiderivative of secant square is tangent. Right, so antiderivative of secant square is tangent, but we're not going to use the limit from 3 to 6. Those limits are for u, not for theta. Right, and also here integral of 1 right. Sorry, integral of 1, so that's d theta, but then again it's not yet. So go back to the problem. We did let theta u equal to 3 secant theta, right? So from here we can solve for secant theta equal to u over 3. Right. What is the ratio for secant? Secant is reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. Right? Hypotenuse over adjacent. So the opposite therefore is going to be equal to square root of u squared minus 3 squared. Usually it's something resembling the problem, by the way. Right, and we need tangent, opposite over adjacent. I don't know why I put the square at the bottom, but just divide by 3, sorry. Right, so that is tangent. And here, since secant is equal to that, we can say that theta is secant inverse of u over 3. Right, so put those two into here, and we have 3 the tangent is equal square root of u squared minus 3 over 3 3 square, and then u equal to 3 to u equal to 6, and theta is secant inverse of u over 3 from 3 to 6. Right. And then we're going to put 6 in, and then we're going to put 3 in. Right, we take some space. So first we're going to put 6 in. Let's do a 3 outside. Sorry. Square root of 6 square minus 3 square over 3 and then we subtract where we're going to put 3 in. And then we subtract. We're going to put 6 in. Just put the parentheses. Secant inverse, where we're going to put 6 in for u, and then subtract secant inverse. We're going to put 3 in for u. Right, so that put the upper limit, put the lower limit, and subtract them pretty much. Now, 3 square minus 3 square, that this term goes to 0. Square root of 6 square, 36. Minus 3 square is 9. 36 minus 9. 36 minus 9, 27. Over 3. Subtract. Secant inverse of 2 minus the negative plus secant inverse of 1. Right, so what is secant inverse of 2 and secant inverse of 1? Secant inverse of 2 is equal to what? We don't know. Let's say that equal to, I don't want to use x, you say z, right? Take the secant on both sides. So we have secant inverse of 2 equal to secant of z. Secant cancel secant inverse. We have 2 equal to secant of z. And secant is reciprocal of cosine, right? And flip both sides. So cosine of z equal to 1/2. Make this a fraction and flip both sides. So z will be equal to cosine inverse of 1/2. So when I need that, I can use the calculator. Usually inverse I will keep in the degree mode. Cosine inverse of 1/2, 60 degrees, which is pi over 3, right? And what is secant inverse of 1? Right, try the same thing. Secant inverse of 1 equal to z. Take the secant on both sides. Secant inverse 1 equals secant z. So we have 1 equals secant of z. And secant of z is 1 over cosine. So cosine of z is 1. So z is equal to inverse cosine of 1. Right. Those are the calculation. Because the calculator doesn't have the cosecant, secant inverse, so we have to go to cosine inverse. That's 45 degrees, by the way, which is pi over 4. Right. Right, so put all together, we have 3 square root of 27 is square root of 9 times square root of 3, which is 3 square root of 3. Right. 3 and 3 cancel out. So we have 3 square root of 3 minus pi over 3 plus pi over 4. Right, so that's what we have. Right, let's take a 5-minute break. We continue at 9:08. Remember, I have a meeting at 10 o'clock, so I'm going to leave right about 9:40, 9:45. Right. You mean up. Yeah, the problem is really complicated, and I make a silly mistake at the end. Sorry, because cosine inverse of 1 actually is 0. Just equal to 0. Sorry. A little bit better. So we don't. Yeah. So. So the answer is just 3 square root of 3 minus pi over 3. Sorry, should be that. By the way, let me zoom back in. Oh, I won't ask you this kind of problem on the test. That's why we do this in class and not doing the test. I try to not put this kind of problem on the homework either. On the test, what I really want you to do is, as mentioned before, if you can turn the problem into just one trig function. I mean, when we make the proper substitution into a trig function, that's why I ask you on the test. I won't ask you for the complete problem. Let me zoom back in a little. Not to focus, sorry. Too much. Right. Once again, what I asked you on the test is something like this. When you make the substitution, you end up with a trig function. Yeah. Because the rest is go back to the section 3.8.3 where we do the trigonometry integral. Right, by the way, at least let's check. I'm going to type that problem on the calculator. Math number 9. I have to go from 1 to 4. And we have a fraction square root x squared plus 5x 4x minus 5 divided by x plus 2 and dx. Yeah, take some time. Yeah, actually check that during the break and I found there's something wrong. Anyway, and then we type this answer. Yeah, I think that's close enough because the calculator, when they do the original problem, there's some small rounding error. So that's pretty close to each other. Yes, so on the test, what you just need to know for this section is, can you get to where you have the trig function, where you make the substitution, everything works out. Can you go back to just the trig function? Because from there, that point on, that is section 8.3. There will be a lot of other things which I already test you in test 1. Sorry, once again, second inverse is 0. So that is 0, that is 0. So we just have that. Right. With that, we go to section 8.5, partial fraction. Right, talking about tedious, the next section is even more so. However, the concept is not as important. I mean, it's not as difficult because the partial fraction we already did in pre-calculus. Right. Like I said, this is in pre-calculus already. So we're going to have, I'm not going to write all 4 cases. Not complicated here. Right? Just jump right into the example. Just want to do one big problem in general. Let's say we have something on the top. I just write numerator. At the bottom though, let's see. Yes, it is in pre-cal, yes. But of course, in this case, after we do the partial fraction, we will do integral. So the idea of the partial fraction is, after we know the partial fraction, we're going to turn this, break this fraction into, that problem over there. We're going to break this into a bunch of little fractions where we integrate each little fraction. So partial fraction, the idea is simple. Let's say we have x minus a to some power m, and then another quadratic, let's say to the n power. Right, so we try to break this into a bunch of fractions. So to do that, we look at the linear factors. There are m of them. So we're going to start with 1 x minus a to the first, not 1, just a fraction first, and then to the second, all the way to the m power. At the top, we're going to have the coefficient, let's say a0, a0, a1, all the way to, this would be m minus 1. The top coefficient doesn't matter. We not need that for further. Alright, so that's for the linear factor. For the quadratic factor, that continue, by the way. We start with the first power. And then increase the power. On the way to that power of n. Now, the difference between the linear factor and quadratic factor is that the top will have 1 degree less than the bottom. So degree 1, the top has no power. Degree 2, the top should be power 1. So we're going to have b naught x plus c. The bottom has x squared, the top has 1 less power, just x. And then b1 x, c1, all the way to b of, this should be n minus 1 x plus c n minus 1. So don't get too hung up with the coefficient, because usually we will not need that much. So the first part of the partial fraction is breaking up the denominator, breaking them down into a bunch of fractions. And then the second part will be determine the coefficient. Now this will only write the form of partial fraction. We do not find the coefficient yet. Right. First one, 2x minus 3. X minus 1. X squared plus 5. By the way, the partial fraction, the quadratic factor here have to be irreducible, meaning it cannot be factored any further. Not only that, it cannot be factored in terms of real numbers. So that means they have no solution. Has no real solution. Because technically, for example, if we have x squared minus 3, we still can factor that out as x minus square root of 3 and x plus square root of 3. So this will not work because it has the solution of plus or minus square root of 3. We have no solution. So that one is not, we should say, irreducible. In precisely, cannot be factored with real numbers. So that precise that. So irreducible or cannot be factored with real numbers, or that equation has no real solution. Right. Like x squared plus 5, the solution will be plus or minus square root of 5i. And imaginary there. Of course, it's not real. So we're good. Right. Now, this we just write the form. So we have a linear factor. And then the quadratic factor. The top, the power will be 1 less than the bottom. If it is x minus 1, the top will have no power, constant. If it is a quadratic, the top will be a linear function, mean the function of x. Right, 2. Usually we cannot have too much of this. I mean, the denominator will not be that complicated, because if it is the case, we have a bunch of coefficients that we have to solve for, and that will be complicated, very complicated. Right, so first, a linear factor cube, so we're going to need 3 of them. 2x plus 2, 2x plus 2 square, and 2x plus 2 cube. Because of 3, we need 3 factors like that. So it is a linear factor, so the top will be just a constant. I use different letter instead of A1, A2, A3. Right, next, the quadratic with the second power. By the way, this one is irreducible. If we solve it, no real solution. Oh, sorry, continue. Blood adding. Plus a quadratic just keep increasing the power until we have that power too. Right, quadratic, so the top will have to be linear. So A, B, C, D, E, F, G. So that is the form of quadratic terms and linear terms all together. Like I said, we don't need to solve for the coefficient here. Right, I throw a curve on here because that one is not irreducible. Certainly this one can be factor, so we have to be factor first. Right. So of course we have x plus 4, sorry, x squared plus 5x plus 4. You see there's two intercepts, so two solution, two real solution. That's why it is factorable. And from there we have x minus 2, two of them, and one of each. Right, all of them are linears though, linear factors. So A, B, C, D. Right, so that's how we break up a fraction. Next, how do we solve for the coefficients? Partial fraction decomposition. For the first one, 1 over x cubed minus 8. Right, before we do that, we have to factor. X cubed will not work. Remember, can only be linear factor and quadratic factors. When we have the cube, need to break it down. How to break it down? Well, difference of two cubes. If we have a sum of two cubes, it will be a plus b a square minus ab plus b square. So the way it goes, the way I memorize this thing is, so the first will be the same as that. The second will be opposite as that. And then the next one always positive. Where we go to chapter 10 or 11, I don't remember. We will get there. Actually, chapter 10. When we go to chapter 10, we will do the formula for even more complicated, like a to the n minus b to the n in general. So we don't have to memorize this little thing. Right, so factor like that. Just write that as 2 cubed x cubed minus 2 cubed. Right. A minus b, x minus 2, a square, x square, ab, 2x, b square, 2 square, which is 4. Right. So break it down into fraction, and a square plus ab plus b square usually is, it can sometimes it can even factor out further, but usually it's not. Actually, that should not be factor. If odd number real, that is. Right? Yeah, usually that is it. It will not be factored any further. Right, so break this out. We have a linear factor and quadratic factor. For linear factor, the top is just a constant. For quadratic factor, the top will be a linear function. Right. I'm just going to write this part again. What we do is just multiply by the common denominator on both sides. So we multiply by x minus 2, x squared plus 2x plus 4. That will cancel with the whole denominator here. So have 1 equal 2. When we multiply by this term, the x minus 2 cancel out. So we have a x squared plus 2x plus 4, right? X minus 2 cancel out. And then plus, when we multiply this 2, the x squared plus 2x plus 4 cancel out. So we have bx minus c, bx plus c. That cancel out. And x minus 2. Alright. So multiply it out. Ax squared plus 2ax plus 4a x squared 2ax 4a bx squared minus 2b x plus cx minus 2c. Right? Then we just combine like terms. Right? If you have different color pens, it will be fine. Otherwise, we use this convention, a square, right? So we use 2 lines below it, and we have those 2 terms are x squared. And we factor out the x squared. I just write a plus b x squared. Fine. That's the first one. Next, 2ax, there's an x there, minus 2bx, and plus cx. Once again, I'll factor out the coefficient 2a minus 2b plus c with an x. And then what's left is those constant. Again, I put in the left hand side. We still have 1. Right, now the 2 side equation are equal when the coefficients are equal. By that I mean there's no x squared here, right? And also there's no x. We only have the constant equal to constant. So we have a equal to, a plus b equal to 0. To a minus 2b plus c equal to 0, and then for a minus 2c equal to 1. Right? Now, we can solve this by hand. I prefer to use a calculator. Let me rewrite this into nice with alignment, that is. Right. Now all I do is just do this. Right. We're going to solve the system equation. I assume that you know this already. This is called using the linear algebra method, reduced row echelon form. So second matrix, go to math and go way down to option where it says RREF, reduce row echelon form. And then we enter a fraction. Right, be careful with this. Fraction, we enter the matrix alpha and zoom. Alpha and zoom. We go to 3 rows, hit enter. 4 columns, hit enter, and then OK. So when we do this, we hit and enter, and after that we do not hit the enter key until we enter all the numbers. So the numbers 1, do not hit enter, just hit the arrow. The next coefficient is 1 for coefficient for B. There's no C, so that will be 0. There's no numbers on the other side, that will be 0 as well. Next, 2 for A. Negative 2. For negative, we use this. Negative. And don't use the subtract sign. And 1. And then 0. For A, minus 2C and 1. And hit enter, we should have that. Hit math and convert that to fraction. So we have 1 over 12, negative 1 over 12, and negative 1/3. After we do that, we have A equal to 112. B is negative 112. And C is negative 1/3. And we put it back into this form. I just need to zoom out one bit. Okay. So we have that. A 1 over 12 divided by x minus 2 plus B x plus C right. So that is a partial fraction. It's not that bad, a bit tedious where we break it down and then try to combine like terms. If you have a good bookkeeping type things, type skill, this will not be as bad. So be a little more organized with this, and it should be fine. Right. As mentioned before, I have a meeting at 10, so I think I'm going to stop here. Do you have any question before I end the stream? Right. As a reminder, I already posted test 1 online. You have until the end of the semester to do it. By the way, I increased the time for 2 hours to 2 hours and a half because the problem is a little bit more complicated than I think. So I think that that should be fine. Right. It goes without saying you can use your note. Right. Do you have any question before I end the stream? Right. Other than that, yeah. No, the partial fraction is okay, but when we get back to the integral, yeah, it might be the problem because ultimately we might need to integrate this, which end up being integrate this. So integrating those two. Right. So. Other than that, have a good weekend. See you on Monday.